Hello everybody, and welcome to the first podcast of the European Young Chemist Network, EYCN. Today, we will discuss the latest research concerning chemistry-related topics of high interest to the general public. My name is Mark Kilada, and right now we will talk about a possible solution to lower greenhouse gas emissions. Nowadays, a majority of the population is aware that CO2 emissions are strongly connected to climate change, and increasingly more people demand policies to lower these emissions. But what technologies do even exist or have to be improved upon to achieve goals such as the Paris Agreement? How can we lower the CO2 emissions of major factories, and how can we store excess energy from renewable sources such as solar and wind? One could argue that these two are the main challenges of this century, and some people argue that one of the answers for both might be the electrochemical reduction of CO2. CO2 reduction generally means the transformation of the harmful greenhouse gas into more useful chemicals via electric energy instead of releasing the CO2 into the atmosphere. But how do we capture the CO2? How does the process work on a molecular level? Why is CO2 reduction currently not applied everywhere? And what are the mentioned useful chemicals? To answer such questions, our Austrian delegate Mougel Steiner approached one of the top young researchers in this field, Professor Dr. Victor Mougel from France. They talked about his research and the current challenges for the reduction of CO2 both scientifically and economically. Professor Dr. Mougel obtained his master's degree in chemistry in Lyon and completed his PhD about the synthesis, reactivity, and magnetic properties of uranium complexes in Grenoble in 2012. He then moved to Zurich as a Marie Curie Fellow and began his research in surface organometallic chemistry. He came back to France in 2016 as an associate researcher in the Laboratory of Chemistry of Biological Processes in Paris, before returning to Zurich as an assistant professor in December 2018. His current research topics are centered on the electrochemical transformation of environmentally relevant small molecules using renewable sources of energy and approaches inspired by nature.
So I have here today Professor Mougel from ETH Zurich. It's a pleasure to have you here. And we're talking today about CO2 reduction. Could you maybe outline your research and why it's important to reduce CO2?
Yeah, sure. So CO2, I would say, is a key molecule, and reducing CO2 or transforming CO2 is, in my opinion, very important for three main points. The first one is we need to lower the release of carbon dioxide in the atmosphere. You've all been heard of global warming, and CO2 is one of the main greenhouse gases. So we need to try to limit the release of CO2 in the atmosphere, and using it or recycling it as chemical or as fuel allows to do that because it's not released anymore, but it's kept and used. The second reason is that carbon dioxide contains carbon, so we could use it as carbon source and as an alternative to fossil fuels. And the last reason, you've heard of the rather high amount of electricity that is produced today by intermittent alternative energy sources such as photovoltaic panels or wind turbines. One of the main challenges is to store that energy, and actually we can use this electrical energy to transform the CO2 into CO2 reduction products.
So you already mentioned that CO2 reduction can be used to lower the concentration of CO2, the most important greenhouse gas in the atmosphere. But how do you actually obtain the CO2 from the atmosphere, and how do you then proceed to reduce it?
So the point here, and I think we have to be clear not to promise things that are not possible. Transforming CO2 or reducing CO2 has not the potential to completely solve the amount of CO2 that is currently released, but it can be a part of the solution by transforming a small proportion of the CO2 that is released into chemicals or fuels. So we are talking in amounts that will never exceed 10, 20 or 30%, depending on the different predictions that were made of the total CO2 released. The CO2 that we target to use is a CO2 that is on localized sources of CO2 that are rather important contributors to the amount of CO2 released. And these typically are some electricity generation when fossil fuels are burned, or factories or companies that necessitate fossil fuels either in engines or in oven to generate heat. In all these places, you generate a rather large amount of CO2, and this CO2 could be used on site because we already have large amount and it's localized. These are existing procedures that we could implement, I would say, tomorrow. Taking CO2 from the atmosphere is a field of research currently. Some people are trying to do that. But of course, you can imagine that the challenge is much higher. We have about 400 ppm of carbon dioxide in the atmosphere. So trying to capture this carbon dioxide will cost a significant amount of energy. And before trying to harvest a very diluted CO2, we'd better start with the very localized and concentrated sources.
Okay, so we're mainly talking about direct integration into the processes in factories that actually produce CO2 and utilize this to regain energy and actually store our renewable energy, if I understood you correctly.
Yeah.
If this can be easily implemented in a factory in a normal process, why hasn't this happened yet? And what are the main issues in trying to achieve this?
Well, I mean, issues are on two scales. I would not even say issues, is that limitations maybe today. I mean, the first case is that CO2 reduction is an active field of research. There are still some fundamental problems that have to be addressed to make systems that are not only efficient, but also economically viable. Because, of course, one of the main criteria to implement this system is the cost associated. And currently, there have not been strong either political or ecological incentive to try doing that. So, of course, there is less industries that have already adopted the CO2 remediation strategies. But it's clearly changing. The price for CO2 release is slowly increasing, and more companies have realized that they will have to mitigate the CO2 release and have already started to invest, I would say, almost massively into research for CO2 reduction. So a lot of the big petrochemical groups or big releaser of CO2 have already started to invest into research to develop this kind of programs. So it's, two limitations, some political and economical, but also on the research side, we have not solved all problems. But I'm very enthusiastic with that, and I believe that within a couple of years or 10 years, this system will definitely be implemented at a larger scale.
So you mentioned there are mainly two parts, one being economics or politics and the other one being research. So what do you think should be major incentives that politics should give the industry to further develop such systems?
Well, it's always hard for me to speak of what politicians should do as a scientist because I'm less qualified than they are in politics, and the opposite is true for science. But one of the strong incentives would of course be the carbon tax, because if you tax significantly the amount of carbon dioxide that a company releases, of course there is a stronger incentive to do something with it so that you don't generate negative value by burning fossil fuels. One of the other parameters that is unfortunately out of control of most governments is the price of oil. Because of course, if we generate or if we use CO2 as an alternative carbon source, we are always somehow in competition with the price of oil. And when oil is like it is at the moment extremely low, then it's very difficult to compete with this kind of issues. So that's more or less what I can say for the political point. And the last thing maybe is also the people, I would say, because if the people ask the government to do something or to try to solve these issues, I believe it has an impact. And I do hope with all the current movement we've been seeing, especially of young people, to push the government trying to solve this issue of CO2 release, that we will have more and more political incentives to maybe develop some processes that are not economically profitable, but that are ecologically profitable.
Okay, so then maybe let's talk a bit more about the science part of the reduction itself. So you mentioned that it's a very active field of research and there are still some challenges ahead for the science to be done. What would you say are the key challenges or issues that have to be solved?
Yeah, so it's definitely a very important field of research and many scientists are working on that. One thing I would just like to highlight, especially as being a chemist, is that we are always seen by a good portion of the public as being the troublemakers. And I would actually like to highlight one more time that we are actually more problem solvers than problem maker in this specific case. But in other cases that were related to atmospheric pollution, if you look overall of, for example, sulfur dioxide contents in the atmosphere, they have been significantly reduced since 10 or 20 years, thanks to great advances in chemistry to remove sulfur from oil and fuel. So I believe chemists have really good answers, or can provide part of the answer to solve these problems. So regarding the challenges, one of the main challenge is that carbon dioxide is an extremely stable molecule. So of course, reducing it, making it more reactive, will require quite a significant amount of energy, and you need to limit the amount of energy required to have catalysts, so molecules or materials that will help decreasing the energy of the reaction of CO2 reduction. Another reason another challenge that we have to achieve today, even if we have the catalyst, is that CO2 is a gas, and transforming gases using electricity in the schemes that we propose for CO2 reduction is something rather challenging, because electricity is not well conducted in gases, you know that. You need a conducting media that is typically a liquid to do these reactions. And carbon dioxide has a very low solubility in most liquids, and even less in water that we target as a used being environmental friendly media. So we have to mitigate that low solubility of carbon dioxide. And related to that, one of the biggest issues is what we call selectivity. If you take a typical case study where you have carbon dioxide that is bubbled into a water solution, you can do two things when you try to reduce CO2. You can reduce CO2 to the product you want, or you can reduce water, the protons, H+, that are contained in water, into hydrogen. And this is a side reaction that will utilize your electron, but not produce the product we want. And what we are trying to do, and what many people are trying to work on, is to try to maximize the reduction of CO2 and to minimize the reduction of protons, H+. And the last challenge among that is selectivity within the CO2 reduction products. Once you've reduced CO2 and not the protons, you can reduce it to quite a wide variety of products. You can reduce it to carbon monoxide, to hydrocarbons, either short ones like methane or longer ones like ethane. You can make unsaturated hydrocarbon, ethylene, that has a very high chemical value. You can make ethanol that will stay in water and be directly usable. You really can make a lot of products. And what you want is not to have a mixture of 50 different products, but to try to orientate the reaction towards only one product among the others. So these are the three main challenges, I would say.
So one could summarize this problem in that you have a very intricate and delicate system where you have an electrode that delivers the electricity, which is solid, and you have a medium, which is mainly water, which is a liquid, and then you have the gaseous CO2, and you have a lot of possible reactions due to the energy added. And how do you address actually this complexity in trying to focus it into one product that you want to get?
So we have here two main approaches, I would say. So it's exactly what you said. The challenge is that we react between a solid, the electrode, that brings the electrons, a gas, and a liquid, the electrolyte that conducts the electricity in the instrument we use to reduce CO2, that is called an electrolyzer. So a lot of the challenges that I've been describing are related to this, what we call the three-phase interface between gas, solid, and liquid. And this is where a lot of the chemistry I have been developing and other people have been developing is focalizing. So in this three-phase interface, there is two important parts we can vary. The solid part, the catalytic part. Here is where the reaction occurs. And we design catalysts that are very selective, as I explained before, that are immobilized onto the electrode. So we can work on the catalytic sites at the molecular level to make sure that the catalyst is more or less selective. So this is what happened on the design of where the reaction takes place. But another strategy is to actually tune and modulate this triple phase interface by either making an hydrophobic support so that you have more gas close to the solid, or to utilize a liquid that has less proton to limit this selectivity towards hydrogen that I discussed, etc. So the two approaches are there. Either you change the catalyst site, or you modulate the interface. I would say these are the two big blocks of research.
And you also published, among others, two significant papers last year that mainly highlight those two different approaches and what you can optimize in the process. One being published in Angewandte Chemie last year, where you were the first group that could produce ethanol as the only liquid product from the CO2 reduction. Could you maybe highlight on what your approach was different to previous ones?
Yeah, sure. So for this first paper, it really falls in the first criteria I was mentioning before. It's modifying the catalytic site himself. You mentioned we were the first one to observe ethanol. It's not exactly the case. There were one or two studies just before us, but with a different approach. Our approach here was quite different to what was done before in the field. A lot of the research in CO2 reduction utilized copper, so the typical material we use for electrical wires, utilize copper as a catalyst, the metallic copper. When you do that, it's the only metal that can actually transform CO2 to hydrocarbons or to very small amounts of ethanol, but it's not very selective. So copper is good because it can make these molecules, but it really makes a lot of different molecules. So you have ethylene, you have ethane, you have ethanol, you have acetic acid. You really do have a whole series of molecules when you use metallic copper. The reason for that is that if you take a plate of copper, at the surface, not all the copper sites are the same. On a metallic surface, you always have defects, you have kink sites, you have plenty of different sites that will have a different reactivity. If you have different sites, then you end up in a very large variety of products, which we want to avoid. So the approach we developed was to say, okay, can we actually isolate and just take one copper atom at a time? And this copper atom, we put it in an environment that is the same in the entire electrode. So this is what we call single atom catalysis. We isolate one atom that we put onto a material, in that case was carbon, and we tune the surrounding of the copper to have 4 nitrogen, so that it's known to be a rather good chelating site, capturing site for this copper, so that we have only isolated copper site in this material. If you have one type of site only, then you can imagine you have better chance to have only one type of product, which ended up being the case in our studies where we showed only ethanol. But the main result of this study, and actually the most influential in the field, I believe, is that we showed that this single atom catalysis seems very attractive, and many people in the field are now working in trying to isolate single atom. But what we could see in the specific case of copper is that when you use it, the copper doesn't stay as a single atom. As soon as you operate it with an electrical potential that is applied, so under CO2 reduction condition, the copper starts to migrate on the electrode surface, gather, and form copper nanoparticles. And we could only do that by observing the catalyst while it is working, what we call in situ. As soon as you stop operating the catalyst, the copper came back to the original single sites. So the main impact was to show that the image we can have of a catalyst before we use it might be completely different from the catalyst during use. And I think this was the biggest influence of this article, beyond the production of ethanol, that is indeed very interesting as it's an easy to valorize product.
Maybe a side question. You mentioned that with other catalysts, you get a broad range of products.
Mm-hmm.
What makes a very specific selectivity for one product better than maybe an overall higher yield of the CO2 reduction?
The main reason why selectivity is important is that once you have a mixture of products, you have to separate them. And this has usually a very high associated cost. Some products are rather easy to separate because the processes already exist from the petrochemical industry. So when you talk hydrocarbons, they know how to separate it, but still there is a significant cost associated to separate these molecules. So the higher the selectivity is, the cheaper the reprocessing and the use of the compound will be. This is the first reason. The second reason is that among your series of products, you might have some that have no economical value or that can be toxic. So if you can direct your reaction to the most valuable products, then you save a lot of energy and you save a lot of money by making a more economically viable process.
And what would you consider are the best products to gain out of the CO2 reduction and why?
So it's hard to say the best. I would say the best available products today are ethylene and ethanol, I would say. But it always depends what you're talking of. If you just look at the final product of the reduction, ethylene is a perfect target because it's utilized at a huge scale to make polyethylene in particular. We are talking of kilograms per inhabitant per year. So it's one of the main commodity chemical, and currently it comes from fossil fuel. So of course, if you can replace the origin or the source of ethylene from fossil fuels to carbon dioxide, the process is extremely ecologically interesting. Ethanol is the second one for two main reasons. We already know how to separate ethanol from aqueous solution like the electrolyte is. We already know to valorize ethanol because ethanol is largely used as a fuel, especially in some countries like Brazil. You can almost replace petrol by just ethanol. And the structure is already there. So having the possibility to make ethanol from carbon dioxide is very valuable. So these are for the primary product that you can directly use. But I would say that carbon monoxide, that is probably the simplest product to make from CO2, has also some interest because we know other chemical processes, in particular one that is called the Fischer-Tropsch synthesis, that allows taking carbon monoxide and transforming it to longer alkane chains that could be used as fuel or as chemical later.
So you mentioned that especially ethanol can also be used as a fuel again and therefore be burned. So would you consider, if you talk about the CO2 reduction to ethanol, that the whole process is more of a storage of energy, of renewable energy sources?
Well, the term of storage is always to be taken with care, because if you use it as a fuel, it will be only a transient storage, because in the end it will be released in the atmosphere. But still, it is fuels that you've not burned, so you've not brought extra CO2 than would have been released otherwise, but it's only a transient storage. But I do believe that on the long term, fossil fuels or burnable fuels will very likely be strongly reduced for transports. And so if you use ethanol for the generation of chemicals or materials, then it's not necessarily released in the atmosphere, and it's indeed a storage.
Okay. So you already mentioned that often it's a challenge to get the CO2 to the catalyst surface.
Mm-hmm.
I think you very nicely outlined last year with your paper in Nature Materials one approach on how this could be solved, where you developed something that increases the CO2 concentration at the catalyst surface by a very innovative design of the cathode itself, actually. Could you maybe elaborate on this?
Yeah, so this work was very related to the second aspect I was mentioning before, modulating the interface between the gas liquid and the electrode surface. And we started here by two observations. We really realized that we need to keep the carbon monoxide close to the electrode to make more advanced products that contain more than one carbon. The other thing we realized was that one of the main challenges, as I mentioned, is to reduce CO2 and not to reduce the protons of water at the electrode. But because there is very little CO2 solubilized in water, if you just apply the saturated CO2 water solution to the electrode at the catalyst, you have much more protons from water than carbon dioxide. And then it's very difficult to selectively reduce the carbon dioxide and not to touch the protons that are all around and in a huge excess. So our reasoning was the following. If we can try to make the interface, one, capture the CO2 reduction products that are gaseous products, and two, have a higher concentration of CO2, then maybe we can solve the two problems in one. And the approach we had was to say, okay, can we make electrodes that maintain a small gas layer just below the places where the reaction takes place? In other sense, can we bring more gas at this three gas phase between liquid, solid, and electrolyte? And we took for that inspiration of an animal. So a lot of the chemistry I do is inspired by natural system. We looked at a very specific spider that is called the diving bell spider that can solve more or less this exact challenge. I don't know if you've seen these spiders in the past, but they are spiders that can go underwater, but they cannot breathe underwater. So the way they do is that they capture all around their body a bubble of air so that they can breathe underwater. This is a quite challenging task to retain a bubble around the body of the spider. And the way the spider has evolved to do that is by having hairs onto his abdomen, and these hairs are hydrophobic. What does it make? It pushes away the water from the abdomen because they are hydrophobic, they don't like water. But because these hydrophobic surfaces are on hairs, they act like pillars that pushes the water away from the body and leave air in between the body and the top of the hairs. we've tried to mimic that feature by taking hairs or pillars that were made of copper, we call that copper dendrites, and to make them hydrophobic. So we had an electrode in which we could have the material, the copper, porous part where we have a lot of gas, and the tip of these pillars of copper where the reaction takes place. And by doing that, at the place where the reaction takes place, we have much more carbon dioxide than protons, and then we can direct the selectivity towards CO2 reduction and not proton reduction. And because we had this gas phase close to the interface, the reduction product would also stay much longer close to the reaction sites. They are not released as bubble in solution, but they stick to the electrode. And by doing that, we have more CO2 that is transformed to a C2 product, a product that contains 2 carbon, and in that case was ethylene.
So you highlighted a very nice approach, and the design of the cathode is actually also very important, not only the material it is made of. To increase the local concentrations, was this the first approach to increase the concentration locally, or are there also other approaches?
There are several approaches that have been investigated in trying to modulate the ratio between CO2 and protons, H+. Because this is the big challenge. We want more CO2 and less H+ where the reaction takes place so that we can reduce CO2 more selectively. What we've been proposing to do is to do that by enriching the amount of CO2 at the active site. But there is a big approach that has been proposed 2 years ago by the group of Ted Sargent at the University of Toronto, which is to say, okay, if you want to have less protons at the reaction site, why don't you use just more basic media? So what Ted Sargent did is that they utilized a very basic electrolyte made of concentrated NaOH, so that in a concentrated base solution, you have very little protons available, and it allows you to really be very selective in reducing CO2 and not protons. So this was a very big breakthrough in the field, alternative to what we do, and maybe we can combine both approach. One of the main challenges they had to face, and it's still a challenge in the field, is that if you take a very basic solution, you have a lot of hydroxide ions, and hydroxide ions react with CO2 to form carbonates. So you consume your reactant, and then you destroy your electrolyte media. So to avoid that, you really have to tune very finely again the interface between the gas and liquid phase, so that CO2 doesn't cross too much the gas-liquid interface and react to be destroyed or non-catalytically transformed, forming carbonates. So I guess we are many groups working on different approaches, and the answer is probably somehow via a combination of the different approaches that have been proposed.
So you also mentioned a lot of problems that actually come from the solution itself with the H+ and the hydroxide ions, depending on the pH that you use. Is there a specific reason why the CO2 reduction is performed in water, or are there also other solutions?
So water is a very, very convenient media. We could do it in other solutions. So there are solutions with organic electrolytes or using solid-state electrolytes. But water has a huge advantage over both of these. The organic molecules are nice and allow selectivity at the cathode at one of the 2 electrodes. But in an electrolyzer, you have, of course, 2 electrodes. One electrode where you will utilize the electrons to make a reduction, but these electrons, you have to take them from somewhere, and they come from the second electrode that we call the anode, where you have to take electrons from another chemical reaction to then bring them to the cathode. The typical reaction we use is water oxidation at the anode. We can oxidize a molecule of water to make dioxygen, which is non-toxic. And when you do that, you can harvest up to 4 electrons per molecule of dioxygen you release. So it's a very convenient way to have a source of electrons and of protons, because we also need protons for this reaction. So by utilizing water, it's an extremely convenient media at the anode. So if we have the same media for anode and cathode, it's a very convenient way of doing the reaction. And of course, water is non-toxic, available all over the world, so it makes it a very easy and economically viable approach. If you look at organic solvents, you will have the same challenge at the anode that organic solvents cannot solve as easily as aqueous solution. And the solid-state electrolytes that also exist have lower conductivity unless they are heated at very high temperature. So to be viable, you need to heat these electrolyzers at a very high temperature, And then you spend a lot of energy that you would save using the aqueous electrolyte. So that's for these two reasons that a significant number of research groups are now focalizing the studies onto using water as the electrolyte. It has challenges, but it has also huge advantages.
So maybe to sum up, what would you consider are the main challenges in the field as a chemist right now, and what do you think will the future hold in this field?
Well, there are, I would say, challenges will come at several stages. If I stay at a very fundamental point of view, we have still not fully understood the reasons of this selectivity, and more importantly, the way to direct the selectivity for a specific compound. We start to have pieces of the answer, but not a very comprehensive view yet. So we still need to study to be able to design rationally active sites to make the reaction we want. This is clearly a key challenge. The second key challenge is that usually we transform a very small amount of CO2 in these electrolyzers. Most of the CO2 will be bubbled in the solution, so we have what we call the small conversion. We bring quite a lot of CO2 in the electrolyzer, and out of all this CO2, only few % are transformed to a different product, which means you need to recycle the gas phase and to make it cycle several times until the CO2 is completely reduced. So we need to develop better chemical engineering approach to ensure that all the CO2 we bring into the system, into the electrolyzer, is transformed. And then there is, of course, some challenges that will arise from the larger scale industrialization, because it's always challenging to translate a system that works in a lab scale to a much larger scale. So some of the challenges, I may not know them yet, because they will arise when people will go at a bigger scale, try to implement that in industry, and they may come with new fundamental questions to be addressed.
And what is your expectation concerning a timeline in when will we see such systems employed in industry?
It's always difficult questions to scientists. My wish would be as soon as possible, but we don't control all the steps in the development, being either on the scientific challenge I just mentioned or on the political challenges that are quite hard to foresee. Especially at that moment when we see the big issues related to the COVID around the world, I imagine that unfortunately people will tend to forget for some while environmental issues. So I wish it's not the case, but I'm afraid it's not a top priority in most of the political agendas in the future. So I do believe that talking of 10 or 15 years is a reasonable time frame, but it's very hard to tell more than that and to even know whether this will be feasible or not.
Thanks a lot for your interesting insight into your research and also the field of CO2 reduction in general. And thanks for your time, Professor Mougel from ETH Zurich.
Thank you very much.
Hello everybody, it's Mark here again. Now, the next section is a news section. But it's not just about any news, this is about the latest chemistry and science news in this month, in June. So the first news section that we have is about encrypting information in DNA. Due to the exponential growth of data produced by humans and limited space on hard disk drives, researchers are now trying to find new, more creative ways of storing information, which should also be able to be encrypted for secure communication. One way is molecular information coding, which stores information directly within molecules. Chinese researchers now present in Angewandte Chemie an approach on how information can be stored in DNA security. They fold the long DNA single scaffold with hundreds of short DNA strands to form pre-designed shapes. Their scheme is capable of bearing information and providing outputs not in a straightforward predictable manner, and the coded information cannot be read until after the specially designed decoding process occurs. How to use the magical methyl effect. The addition of singly methyl group to a molecule. This seemingly minor structural change can affect important drug properties immensely and is known as the magic methyl effect. However, the addition of such a methyl group can be quite challenging for chemists, but might be needed in a later stage of the drug development process. A team of researchers from Sweden and Germany now present in Nature Chemistry a cobalt catalyst CH methylation, which allows for predictable methylations without any preparation or protection steps in the chemical synthesis. This allows chemists to create slight variations of the same drug to increase its efficiency in a cost-efficient and timely manner. New method to increase convenience and efficacy of antiviral agent discovery. Due to the vast number of possible chemicals to be used as drugs against viruses, the invention of efficient drugs is time-consuming and tedious. Researchers need to test many different possible candidates, and the procedure to validate either the success or failure of a potential drug can be quite complex. Now, South Korean researchers published a graphene-based fluorescent nanosensor in Science Advances. Their newly developed system can be employed in high-throughput chemical screenings to identify novel, direct-acting antiviral drug candidates, which can speed up the development of new drugs, even for difficult targets such as proteins of RNA viruses. Hello everybody, it's Mark Kilada here again. We hope you enjoyed our podcast and stay tuned for our next edition. This was the first podcast of the European Young Chemist Network, EYCN.